In this video lecture, we're continuing the chapter on coordination complexes, and we're going to cover the section on crystal field theory. This is going to cover different complexes that form and why we see the different colors in solution. So many complexes are richly colored. The color arises from the fact that the complex absorbs some wavelengths of visible light and reflects others. So a quick review of the color circle, which you may have seen before. So this complex iron appears violet in color, so this solution right here, because it absorbs light at the center of the visible spectrum. So what we're looking at, if we see violet color, that means that the solution is reflecting violet and absorbing the complementary color, which is the other side of the color wheel. So absorbs yellow most intensely. And so what we see here, an absorption spectrum, where we have wavelength on X and absorbance on Y. And you can see the complex absorbs. It's really a range of wavelengths. And we look at the maximum color for what is being absorbed. So if I have a solution that looks red, so if I see that it is red, that means that red is being scattered most intensely and green is being absorbed. If I see a solution that is green, that means green is scattered, red is absorbed. So a quick reminder about how these bonds are formed between the metal and the ligand. We have our metal cation, the empty hybrid orbitals on the metal, and then our ligand, remember, that has the two electrons to make that coordinate covalent bond. In this case, ammonia. So I know I've got a coordination number of, I've got 3 bonded atoms, 1 lone pair. That results in a hybridization of sp3. And so we have overlap between the empty metal orbital and the filled sp3 hybrid orbital on this particular ligand. So our resulting molecular orbital is a sigma bond. So remember, a sigma bond is electron density that is shared along the bond axis. So that's a sigma bond between the metal and ammonia. So again, all of our electron density is shared along that bond length. And that's the important part from this slide. So in crystal field theory, we're looking at overlap between the metal center and the ligands. So in this slide, we're reviewing the d orbitals on the metal center, because our metal is using its unoccupied d orbitals to make that new bond. I do want you to be able to draw all of these d orbitals. It's something that is covered in Chem 101. I'm going to review it here as well. So just a quick overview. I can see my dz squared. The orbital is this kind of orange shape, yellow shape in the center. So dz squared, notice it's on the z-axis. So my dz squared is on the z-axis, and squared, it's on axis. Dx squared minus y squared, the orbital is on the xy axis. If I have my dxy, it's on in my xy plane, but notice how the orbitals are between the axes. My dyz orbital is within the zy plane, and again, it's between the axes. My xz orbital is within the xz plane and also between the axes. So we're going to go over now how to draw these orbitals on your own. So we'll start with our dz squared orbital. And you can draw these even if you're not a good artist. The key is just to rotate the axes that you're looking at. And we can make, because all of these orbitals are in just one plane, we can make these as just two-dimensional drawings. So for my dz squared orbital, the important axis is z. I'll label the other one x. It could be y, it doesn't matter. And again, z squared, it's on the z-axis. And it looks like kind of like a p orbital with that donut in the center. So this is our dz squared, and this would all be shaded in. There's a node in the center between x and y. Let's look at the dx squared minus y squared. So the xy plane is what's important. X, y. This is dx squared minus y squared. And again, it's on the xy axis. And it looks like two p orbitals. Perpendicular. And this would also be shaded. So all of these will be shaded inside. So the orbital just shows where you're most likely to find an electron. And now the dxy orbital is, again, the important plane is our xy plane. And the orbitals that are not squared are between the axes. And it's going to look something like this. So the exact same shape as the x squared minus y squared. The difference, these orbitals are between the axes, not on. For the yz, we have the exact same drawing. So for dyz, the important axes are y and z. And again, I'm between the axes, so it looks identical, just on a different plane. And lastly, dx. So my important axes are x and z. Same exact drawing. And that would all be shaded in. So it's important if I am discussing the, for example, dyz orbital, you know what I'm referring to, that shape, that plane, and between the axes. And I took the time to redraw these because I want you to be able to do this on your own and also understand that the orbitals aren't that complicated to draw. I think what makes it easier is make sure, just rotate the axes that you're looking at. Don't try to draw in 3 dimensions for these. And again, the reason this is important is because our metal cation center uses its unoccupied d orbitals to create these bonds. Now let's look at the energies of the d orbitals in an octahedral crystal field. So what we're looking at over here, these are the orbitals in a free atom. That means, for example, just maybe iron 2+ by itself with no ligands around it. And then what happens as my iron gets put into an octahedral field, so maybe now we're looking at FeH2O6, so 6 aqua ligands, 2+. I know that's an octahedral geometry because I've got 6 monodentate ligands. So now my metal center, my iron 2+, I still have iron 2+, but it's no longer by itself. It has the aqua ligands surrounding it. And remember, in an octahedral shape, what's happening? So let's draw this here. So Fe in the center, line, line, wedge, wedge, dash, dash. And let's note these axes, Z, X, and Y. So any ligand, and our ligands come in as point charges. So let's go ahead. I'll draw my aqua ligands, OH2, 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 H2O, again emphasizing that oxygen is the donor atom. So all of the ligands come on the axis. So any orbital, any d orbital on the metal center that is on the axis is pushed to higher energy equivalently. So my dz squared orbital and my dx squared minus y squared orbital end up at a higher energy. They're no longer degenerate with the three below. So my dxy, my dyz, and my dxz, remember all of these orbitals are the exact same shape and all between the axes. So they are all degenerate in the lower level. So again, a metal by itself, remember all d orbitals are degenerate or the same energy, but in an octahedral field, this is no longer the case. Any orbital on axis is shifted to higher energy because my ligands are all on the axis. Any orbital between the axis is shifted to lower energy. And now we have what is called delta right here. So that is the energy difference between the lower and the upper d orbitals, and this is referred to as our crystal field splitting energy. So delta is our crystal field splitting energy. And if you remember from Chem 101, if I have an electron at a lower energy, what I can do, I can put energy in, promote the electron to a higher excited state for a moment. As the electron comes back down to a lower excited state, it will release energy in the form of light. And our energy equation from Chem 101, remember E equals hc over lambda, where h and c are constants, lambda is your wavelength. Well, for Chem 102, we'd use the same equation. But in this case, our energy is our crystal field splitting energy. And we'll look at some examples there in a minute. So what's important in this slide, again, is a metal by itself. The d orbitals are degenerate in energy, all 5 of them. A metal in an octahedral field, the d orbitals are no longer degenerate. Any orbital on the axis is shifted to higher energy because our ligands are also on axis. Any orbital that is off axis is shifted to lower energy. And now the difference between the lower and the upper energy levels is called our crystal field splitting energy. And we can use this equation, delta equals hc over lambda, for a given wavelength to find energy and vice versa. Remember, h and c are constants. So here's another example with that. So in this case, we're looking at the 3d electron of hexa aqua titanium 3. So I know that aqua is neutral in charge, so titanium must be plus 3. And if we look at our periodic table, Ti3 plus is a D1 metal. And that's why I have this one electron in the lowest energy orbital. So the 3d electron of hexa aqua titanium 3 is excited from the lower energy d orbitals to the higher energy ones when irradiated with light of 495 nanometer wavelength. So you apply energy of a specific wavelength, the electron gets excited and promoted to a higher energy. This electron is no longer, it's not as stable at that higher energy, so it will go back down to a lower energy, and when it gets back down to the lower energy, it will release energy in the form of light. And again, this is our Chem 101 equation. We can see here, again, a reminder of going from the identifying the oxidation state of the metal center, and then figuring out how many d electrons. And now we can see why that's so important. So when we draw a crystal field diagram, which will look like this, you'll need to be able to add the correct number of d electrons based on the oxidation state of the metal center. So let's look at practice exercise 3. Estimate the crystal field splitting energy for a red solution of hexacyanoferrate 3 ion. So I know I'm going to use my equation, delta equals hc over lambda, because we want to estimate the crystal field splitting energy. And remember, this is delta. So delta is what we're trying to find. H and C are constants. They'll be given to you on an exam. So H is 6.626 times 10 to the negative 34th joules times seconds. That's Planck's constant. C is the speed of light. And lambda has to be in meters because there's units of meters hidden within that joule. And also it's going to cancel with the meters in our meters per second from the speed of light. It's very important. Add to this lambda absorbed is what we need to use. And this goes back to the color wheel that we saw in the start of this lecture. So if I see a red solution, that means the scattered wavelength is red. That means the wavelength absorbed is the complementary color, right? Which is green. And a reminder where that came from, if I can get back to this first slide quickly. Our color wheel. So if I see a solution that is red, that means it is reflecting red, absorbing green, and that's the wavelength that we need to use for this problem. So I'm absorbing green, and I would give this to you, that the midpoint of green is 525 nanometers. So the first thing we're going to do is convert 525 nanometers to meters. And remember that 1 meter contains 10 to the 9th nanometers. And I can just as correctly say, remember how these prefixes work, or how algebra works, 10 to the negative 9th meters, and it's the same as 1 nanometer. So both of these are equivalent, and you'll get the same answer. And now we're going to use our equation to solve for delta. So delta equals hc over lambda absorbed. So Planck's constant. Times the speed of light. Divided by our wavelength absorbed in meters. So our crystal field splitting energy comes out to 3.79 times 10 to the negative 19th joules per ion. And something that's really important to remember, the units for delta are always in kilojoules per mole. So once we get our joules per ion, I can convert. I know that there's 1,000 joules in 1 kilojoule. Make that more clear. And so my units of joules cancel, times one more conversion to convert ions to moles. So I know in 1 mole, I have 6.022 times 10 to the 23rd. So Avogadro's number of ions. And now I can see my ions cancel. And now when I multiply and divide through, I end up with 228 kilojoules per mole of ion. So a quick recap, we're asked to find delta. I know I'm going to use delta equals hc over lambda. You need to remember that stands for lambda absorbed. H and C are constants. To find lambda absorbed, we see that the solution is red, therefore the color that is absorbed is green, and I would give you what specific wavelength to use. So we're using 525 nanometers here. So I first convert to meters. I then plug that into my hc over lambda equation, and then remember to convert from joules per ion to kilojoules per mole. And make sure you can get this answer on your calculator.